Kamoun for the introduction. I also thank you. I also thank the organizers for giving me the opportunity to participate in this very interesting event. So my presentation will be about highlighting and pointing out the challenges and the trends related to security and privacy in this new context of IoT. I will begin by showing you this slide illustrating how the internet was architected in the very early phase in the DARPA in the US. And you see that it is a very simple architecture. But now, some decades later, look at the connectivity graph illustrating how the terminals, servers, hosts, all of these components are interconnected throughout the internet. So the complexity of the internet is growing exponentially. And this also illustrates how, in terms of the protocol stack, the internet has evolved. First, there was a big concentration of protocols at the application layer, at the physical layer, but all of them went through the IP protocol. This was the heart and the core component of the internet. But now, after certain decades, we have some busy and a bottleneck, a sort of bottleneck in the central part of the internet. And this completely transforms the shape of the internet. So this traditional 7-layer model, it is very well adapted to client servers, 2-tier, 3-tier, N-tier architecture, but not adapted to the context where smart things that can be cars, RFIDs, smartphone, robots, when all of these become connected to the internet, and more precisely, when they become autonomous in terms of decision making, the 7-layer architecture is no longer compatible. That's why several models have been proposed in order to represent how the Internet of Things should look like. Of course, multiple models, 4-layer, 6, 5. This is one of the models. It is the most detailed one, but not necessarily the most popular. And you see that in addition to the traditional, to the traditional layers of the internet, we have here a layer for the physical devices and controllers. And as I pointed out earlier in the presentation, the new thing here is that they will become autonomous from their connection to the internet. So they are connected, they can collect data, they upload data on the internet, but also they communicate with other objects. So these will also be able to connect in machine-to-machine scenarios. So we will have new scenarios that will connect these things, the traditional encapsulation, decapsulation, but also the M2M that will bring new opportunities and new challenges. We have some layers in charge of aggregating the data, in charge of pre-processing the data before sending on the internet in order to optimize the use of the bandwidth resources offered by the different kinds of gateways. And also, third very important part, it is how to process the data, because the data will be big in terms of volume, but also characterized by a high velocity and a high variety and a high heterogeneity stemming from the fact that we will interconnect different things, different applications to the same ecosystem. As an extension to this thought, some analysts tried to illustrate the evolution of the internet. And one of the questions that was raised in an interesting article published in 2016 is if the internet was a country or an economy. The answer is that it would rank 5th in the world in terms of GDP, in terms of gross domestic product. So this tells you about the volume of business created around the internet. But I extend myself this reasoning and I bring another question. What if instead of using the GDP, we use 2 other indicators, the net national product and the gross national product? What's the difference between GDP and NNP and GNP? And what do these indicators have in relation with technology? The answer is that GDP is mainly related to geographic region. It is the border of the country, the GDP of the country. Unlike the two other indicators that are related to citizenship. So they take into account in the traditional economy, they take into account offshore companies, for example, that are not geographically in your area, but they are creating animation of the economy of your country. In traditional economy, there is a difference, but when speaking about the internet, which is natively a cross-border network and an international network, how can we deal about these, or the extension of this reasoning from GDP to GNP and NNP? And the second question, which is more related to the Internet of Things, is how the notion of citizenship will be represented when we will speak not about humans, but objects. My car that will create business, for example, by selling or by uploading the data from the GPS to other applications in order to create added value that will be sold to a company. These are new business models, and the notion of citizenship, when speaking about object, is new in terms of technology, of course, but also in terms of legal and jurisdictional aspects. So the evolution from the internet to the Internet of Things is creating very new challenges, are very interesting opportunities to look at. These challenges are represented here. So these are not the security challenges, but some of the challenges related to the evolution from the internet to the Internet of Things. First one is scalability, how to deal with this exponential growth of things, of the scope of the application, of the diversity of the application. All of these are growing at a very big pace, and the evolution of the technology is not necessarily following the evolution of the needs and the evolution of the concrete world. Also, discovery. Discovery is very important because at the physical layer, if you remember one of the foregoing slides, at the physical layer, one of the tasks of the object will be not only to communicate, but also to gather data and to discover the environment. And since the object will be autonomous in terms of decision, this autonomy has to be in conjunction with context awareness. So the object has to act and react and to decide in terms of, or in accordance to the evolution of the context, of the dynamic context. It can be temperature, it can be physical location, it can be time. So all of these are part of the dynamic context, and the object has first, before doing the processing, it has to discover. One of the problems is how to do discovery, especially if the objects are deployed in a non-trusted or in a non-secure area. So this becomes a very big challenge. Third one is performance. Performance stems from the heterogeneity of the objects. These can be, as I told you, cars, robots, very tiny sensors, and this heterogeneity makes that the algorithms that will be developed on these objects have to adapt to the resource in terms of CPU, memory, storage of the objects. So we have generally now asymmetric models between the infinite growth of the resource in the internet, especially with the growing of quantum computing. And last year, the first quantum computer, completely quantum computer was devised in a laboratory environment. So these things are coming. So there will be some infinite resources in terms of storage, CPU, and memory at the core side, but our objects are very resource impoverished in comparison to this core component. So one of the problems is how to deal with this asymmetric distribution and unfair distribution of performance. Also, the harmonization of standards, and Professor Jan already pointed out the importance of standardizing the different components of the Internet of Things. And last one is big data And data is very important now from the economic point of view, because it's creating some new economic and new business models that did not exist before, especially the data brokering mechanism. And the fact of dealing efficiently with the data and extracting relevant information from the data is very, very important, because the volume of the data, its variety and its velocity will prevent existing mechanisms in terms of data science from doing the right job with respect to these requirements. Now I come to the security challenges that I will highlight. I will begin by saying that the advent of the Internet of Things is creating a nice ecosystem for the attacks to flourish. So it will create very significant challenges for people who are working in industry or research in the security area. And this is to tell you that the Internet of Things cannot be thought of separately from a complete landscape in which we find, in addition to the Internet of Things, cloud computing, social networks, and big data in terms of research niches. Why? Because, for example, if you look at social networks, their interaction with the Internet of Things is that they can create new interaction models between the objects. So there are new social models that are unlike the traditional models using on the Internet, the client server and these similar models. Now we have the communities, and we can speak about communities of objects that will create new attack vectors. And last year, in 2016, there was two very big distributed denial of service attacks against hosting companies in France and in the US. And according to some analysts, the bandwidth of these denial of service attacks exceeded for the first time 1 terabyte per second. So imagine the volume of the data. It's very big. How can we reach this volume of data to attack a single infrastructure? The answer is that they used the connection of some things. In this context, they were surveillance cameras that which can upload very huge volume of data in order to attack the victim. So these new types of connection in terms of social network between the connected object can be used as a vector in order to accelerate or in order to amplify the impact of attacks, including, for example, denial of service attacks. Some other challenges related to the IoT itself is that multiple objects don't have even an IP address. They just have a pseudonym. And the way to connect or to interact with this object is not easy, because many of the identification, authentication, confidentiality protocols used on the Internet rely on the IP address. So it will be difficult to incorporate or to integrate objects that are not identified as supposed by the Internet protocols in the Internet ecosystem. I already highlighted that. Also, it's very important to know that in the Internet of Things, there will be very important variation in terms of dynamic context, in terms of time and space. This one is very important, risk sharing. It's brought by cloud computing, because some part of security is about identification, analysis, and assessment of the risk. Before taking the decision and before implementing the decision, I should know the risk taking from the existence of the attack or from the existence of the vulnerability, and then I choose the right countermeasure according to the level of risk. But unlike traditional information systems, in cloud computing, the cloud provider shares the risk with other parties, including the owner of the data, the host or the hosting company, the developer. So all of these actors are sharing the risk, and these are new models in order to integrate how to take the decision about which security solution or which security countermeasure is better for a specific context. In terms of big data, The challenges are basically related to the complexity of the cryptographic routine. For example, if you have a very huge database and you want to scroll across this database in order to execute a basic query. And imagine that this database is encrypted, is fully encrypted because of privacy concerns. The question is, if in order to execute the query, of course, I cannot execute it roughly on the encrypted data. I have to decrypt first, look for the correct output, and then re-encrypt. If this database is about millions of lines, this will take a huge time, and this is not good in terms of performance. That's why some new models are considered here. For example, homomorphic encryption, identity-based encryption, all of these are being investigated in order to solve how to deal with the complexity of cryptography when dealing with big data. This is in addition to the multiple processing needs. There are new needs, for example, aggregation of the data, search, and the new scenarios that we can execute in order to extract, as I told you, information from the data, which is not easy in terms of data science. So in terms of traditional life cycle of the data, generally we have these 7 phases, beginning from the generation, the use of the data, then the transmission or the transfer of the data, transformation if needed, storage, archival, and destruction. This is generally the life cycle of the data from the generation of the data to the destruction. Of course, this depends on the application, and the list is not necessarily exhaustive. It depends on your needs and on your requirements. Some question here is when we will extend this life cycle to the IoT, to the context where the objects will be connected, not only the terminals, the client, and the servers. First one is where to store the data, because now I don't have only the servers that are able to store, but also even the objects have some storage, some small storage capabilities. So how to distribute the storage capabilities across this new scheme and across these new layers and this new architecture of the Internet of Things. Second one is about retention, especially in communication. There's a need for retention of the data. Retention is that I have to satisfy that the data should be available, for example, 1 week or 1 month. It depends on the need. And retention, generally, it is conditioned by some legislation or by some regulation, meaning that by the law, I should preserve the data for a certain period of time. The problem is, since the network will be very distributed, and since the scope of the network will be very wide, retention will become a big concern. Destruction also, auditing, monitoring, and risk management, because we don't know how to audit or how to analyze the risks in a very distributed environment, including different kind of objects, and especially with new business models and the new threat models. Privacy breaches are very important in the Internet of Things because they can originate from multiple parties. Traditionally, privacy, it is related to the privacy of human. It's my data. But we can also extend this thought to speak about the privacy of the data of the object. So the object itself will have some private data. And the big question here is who will be responsible for protecting the privacy? Which actors can we implement in order to protect the privacy of all of these data? 2 minutes. I will skip over this. So I will finish by highlighting some open problems so that people can, that interesting people can identify some niches to work on. A very important problem is privacy versus lawful interception. Lawful interception is a very interesting functionality especially for telecommunication operators. And even from the legislation point of view, it is part of the Budapest Convention. This is the capability of the law authority or the law enforcement authority to extract data from an ongoing communication. So it is lawful interception. It is the capability to intercept the communication. Of course, under a very strict scope in terms of time and space. So this is, for example, a way to implement lawful interception in the context of 3G and 4G networks. But in the Internet of Things, different schemes will be possible to communicate between the objects. M2M, which does not go through the 3G and 4G. For example, we can have specific gateways, including LoRa, Sigfox, and these schemes. We can also have voice over IP, which is not covered by this technical scheme for lawful interception. And the problem becomes more complicated when the context requires the anonymity of the object. For example, in medical application, sometimes we require that the data stemming or originating from the object is anonymized. And in this context, we cannot identify, or we cannot do this intrusion, this benign intrusion or this lawful interception in the channel. The second important channel is anonymity versus authentication. For example, one of the very popular tools for anonymity is onion routing. This is the nested routes that prevent, for example, censorship equipment to prevent you from reaching a certain destination, or that also prevent some authorities to identify your identity or your location or something related to who you are. So the problem here is how to combine these two requirements, anonymity and authentication. Authentication is to prove who you are, and anonymity is to hide who you are. In some situations, we are in an obligation to fulfill both of these requirements, and we need new, not only cryptographic algorithms, but also new trust models that are different from the existing models based on PKI, PGP, and the similar models. So we need new trust models in order to implement new security functionalities in the IoT. I will finish with this slide, which presents the very important technical challenge also: federated identities, anonymity, and privacy. Federated identities is when you have multiple identities going through a signal, through a single authorization channel. So you have multiple identities, for example, one password for YouTube, the other one for Facebook, but since you are logged in one application, you are automatically logged in the other application. So your identities will be federated into a single identity using, for example, a signal sign-on mechanism. Now we have some solutions for the traditional model of the internet. But what if, for example, my identities will not be passwords, but will be the identities of the objects connected to me? There will be the identity of my car, of my laptop, of my smartphone. I want to combine all of these in order to have the same profile according to some applications or according to some portals or whatever. The issue is that the operating system will not be the same on all of these environment, and also the computational resources will not be the same. So this is a very important technical challenges that you can address in order to fulfill some significant results. So thank you for your attention. I hope that you enjoyed the presentation.
Thank you very much for your